Welcome to Power Electronics lecture. Today we will start the new unit, inverter. So what is the inverter? In general, inverter is a device which converts the DC power to AC power at certain output voltage and frequency, or it may be at certain level and frequency. What is the use of inverter in industrial application? In industrial application, it can be used in variable speed AC motor drives, induction heating, UPS, HVDC transmission lines. Generally, inverter are two types: VSI voltage source inverter and CSI current source inverter. In our syllabus only VSI is there, so we will study only the voltage source inverter. So this is the first topology, single phase half bridge inverter. Single phase half bridge inverter. So this is the circuit diagram for single phase half bridge inverter. It consists of the two thyristors and two diodes. This supply each DC supply is converted to two different supply, VD/2 minus VD/2, by using two capacitors. So here is showing RL load. First we will discuss about the R load. Okay, so how it will work. When thyristor T1 is triggered, means we have provide the gauge signal to thyristor T1, then T1 is triggered for time period T1, means Ty2. Okay, then voltage across the load is plus VD/2 plus VD/2, this, and this is the force coming to the thyristor. At this point the thyristor T1 is off and thyristor T2 will conduct. So this, for this time period the load voltage is minus of VD/2, and this is the alternating. If this is the purely R load, it means current waveform is almost same for resistive load. So this is red line is showing for RL load. Red line is showing for RL load. So at this instant, means if we consider this RL load, then suppose initially this L is charged, that means current will flow through this diode. At this instant T1 is off and D1 is conduct, and current flowing through this path, through the D1. So it will here up to this point, from negative to 0. At this point T1 is triggered, and yes, then again this points from positive to 0, this D2 will conduct. This is the use of D1 and D2 for damping current, flowing for the damping current. But main drawback of the single phase half bridge inverter is that it requires the 3-wire DC supplies. To overcome this 3-wire DC supply, we will use the single phase full bridge inverter. So this is the single phase full bridge inverter. This is the circuit diagram of the single phase full bridge inverter. It consists of the 4 diode, 4 thyristor, RL load, and supply DC. In this circuit, this pair T1 and T2 will conduct together, okay, and this pair T3 and T4 will conduct together. Similar for this diode, D3 and D4, D1 and D2 conduct together. For resistive load, first case for resistive load, if thyristor T1 and T2 is on, the voltage across the load is V0, is positive VD in this fashion, okay, in this fashion. At instant T1 and T2 is off and T3 and T4 is on, then the current will flow through this path, negative VD. This is the alternating. If the resistive load, then current voltage is almost same as the V0, but here RL load. Similar here, if L is charged, then current will flow this diode D1 and D2 in this fashion, okay, in this fashion, from this point to this point, D1 and D2, okay, from negative to 0, D1 and D2 will conduct, from 0 to positive, D1 and T2 conduct, then again positive to 0, D3 and D4 will conduct. So this is the load current IL and output voltage V0. This is the working of single phase full bridge inverter. Due to the square waveform, it contains the harmonics. Let's see. We have seen T1, T2 and D1, D2. For this period, D1 will on, okay, from this to this, and again for T1 from here to here, okay. Output voltage we can find out from this equation. So from the Fourier series we can find out the V0. This is 2D sin n omega t. This is the fundamental RMS output voltage V for fundamental 145 VD. Total harmonic distortion we can calculate from this formula. Okay, now the full bridge inverter. For this period thyristor D1 and D2 will conduct, okay, from negative to 0, and from this D1, T1 and T2, okay. For similar D3 and D4, it is almost sinusoidal waveform is coming, and RMS output voltage we can find out this from 19.5 and 19.6. and output voltage from Fourier series we can find, here we have find out from the Fourier series. So A0 and AN is 0 because of the A is 0, A0 is 0 and AN is 0, again 0 for symmetry waveform, and this is calculated by Bn only. And for the fundamental output voltage V1. This is the working of single phase full bridge inverter. Thank you for watching.